Hello everyone, and welcome back to another episode of Bo Maths. I apologize for the delay in the videos. I've had a really busy week last week, but hopefully we're going to be getting back onto a regular schedule. And today we're going to be practicing our previous lecture video, which was all about prime and composite numbers. So we're going to get comfortable with those ideas before we move on, and in future videos we're going to be seeing more and more as to why we should care about prime numbers and really all of what we've been talking about. So let's get into it. So here are the questions. Please pause the video, give them all a shot yourself first, and then we will proceed. All right, we got question 1. Are the following numbers prime, composite, or neither? So remind me, what did it mean to be prime, and what did it mean to be composite? Well, to be prime meant it had only the factors of 1 and itself. And to be composite meant that it had more than those two factors. So basically, it meant that it wasn't prime. So let's look at these numbers and let us determine. So first of all, we have 31. All right, so 31, well, we can start by looking at its factors and see if we get anything other than 1 and 31. So we know 1 and 31 are a pair since 1 times 31 is 31. Is 2 going to do anything? I don't believe so. How about 3? Nope. Because 31 is not a multiple of 3, right? 3 times 10 is 30. There's an extra 1 there, so that's not going to work. 4 isn't going to work because if we count by 4s, we're going to get to 28 and then 32 passing over 31. 5 isn't going to work since we know that for a number to be divisible by 5, it has to end in a 0 or a 5. How about 6? Well, 5 times 6 is 30, which means that when we go up the next one to 36, we're going to be passing over 31, so 6 isn't going to do it. How about 7? Well, 7, 14, 21, 28, 35. Counting by 7s, we pass 31. And we can try it with 8 and 9, and I encourage you to try these yourself, but if we count by 8s and 9s, we are going to pass over 31. If we look at 10, 10 times 3 is 30, and then we get to 40, so we're not going to have 31. And do you remember what number we're going to be trying up to? We're going to be trying up to 15 because that's half of 31. So we can try all these values, but we aren't going to have any luck with any of them. Simply just take multiples of them, and you're going to find that we're going to pass over 31 in all those situations. So since the only factors of 31 are 1 and 31, 31 is a prime number. All right, how about 34? What do you think? Do you think 34 is prime, composite, or neither? Well, we know 1 and 34 are factors of 34. That doesn't tell us if it's prime or composite yet, though. But what if we look at 2? Well, 34 is an even number, so it's automatically divisible by 2. And if we look, we'll get 2 times 17 gives us 34. So these are two factors other than 1 and 34 that go into 34, which means 34 cannot be prime. It has to be composite. All right, so we don't even need to check the rest of the numbers because we already found factors other than 1 and 34. All right, let's look at 1. So is 1 prime, composite, or neither? Well, the only factor of 1 is 1. Well, okay, so is 1 going to be composite? Well, it can't be because it only has one factor, right? And in the previous video during the lecture, if you recall, we also said that 1 can't be a prime number either. That's largely by the definition of prime numbers where we just kind of exclude 1 from the picture. But if you want more of an explanation on that, I encourage you to go check out the video. All right, and then we have 29. So I'm going to guess that 29 is also prime, but we can go ahead and check its factors. So we're going to be checking up to 14 because that's around half of 29. And if we check 2, it's not going to work because it's not even. 3 isn't going to work because if we add these digits, it won't be a multiple of 3, right? 2 plus 9 is 11. 3 doesn't go into that, so 3 won't work. 4 isn't going to work either since 4 times 7 is 28, so that's not going to get to the 29. 5 isn't going to work since this doesn't end in a 5 or a 0. 6 won't work because 6 times 5 is 30, and that's only 1 off of 29. 7's not going to work for similar reasons, because 7 times 4 is 28, and so we'll be skipping over 29 when we are looking at multiples of 7. And then if you check all the other numbers up to 14, which if you're not feeling comfortable with this yet, I encourage you to check these numbers. Simply take multiples of these. You'll see that we skip over 29, and we will see then that 29 has no factors other than 1 and 29. So 29 is prime. All right, so it's quite the process to kind of like check all these factors every single time. So I would encourage you to like actually memorize which some of the numbers that are prime. You know, you can go through and start making a list of the primes. It'll be like 2, 3, 5, 7, 11, 13. And kind of as you go, just like mentally check for some factors. But as you kind of go, you'll kind of get a bit more of a feeling as to like which one of these numbers are going to be prime and which ones aren't going to be prime, and you can kind of go on from there. So I'd encourage you to memorize some of the prime numbers just so that you don't have to check for factors every single time. But this is how we know that it's prime or not. All right, and then the last one we have is 0. Is 0 prime, composite, or neither? Well, 0 has infinite factors. We discussed this last time because we can do any number times 0 and we get 0, which means that any number is a factor of 0. So that means it certainly can't be prime. But we also saw that having infinite factors kind of made it less meaningful. So we also saw in the last video then that 0 was not a composite number either. So this, like 1, was neither. And I should have wrote neither up here. Right, so again, with the 1 and the 0 case, if you're confused on that, I encourage you to go back to the previous video because I have a full explanation as to why 0 and 1 are neither prime nor composite. All right, and then just for extra practice, pick some random numbers and see if they're prime, composite, or neither. And just keep doing this until you feel comfortable with it. All right, on to number 2. I have a mystery number that's even. Choose the correct answer. Okay, so we have a mystery number. We don't know anything about it except that it's even. And we have 3 options. The number must be prime, the number must be composite, or we don't have enough information to know. So we're saying that the number is even, which means that it has to be divisible by 2. So even means it must be divisible by 2. So it has 2 as a factor. So that's good. So does that mean it's composite since it has 1 or something other than itself as a factor? Well, not quite, because we don't actually know what this number is, right? If the number was 4, that's an even number, then yeah, it has 1 and 4 as a factor, and it has 2 as a factor because it's even. So that means this would be a composite. So we might be leaning towards B. However, what about 2? 2 is also even, right? And its only factors are 1 and 2. So that means 2 is a prime number. And in fact, 2 is the only even number which is also prime. So if we think about that, then we also could have a situation where this mystery number we're talking about, in the case where it's 2, is a prime number. So A is also possible. So we've just shown a situation in the case of 4 where our number is composite, and in the case of 2 where our number is prime. Since we have no other information other than the fact that this number is even, we have to go with option C. We don't have enough information to know. All right, moving on here. Josh claims that he has a prime number that's divisible by a whole number. Kieran thinks that's hogwash since primes aren't divisible by anything. Is it possible that Josh is correct and Kieran is wrong? Alright, well, this one is just kind of a matter of understanding the definition of a prime number, and it might be a little bit of a trick question in the wording, because this is saying that I have a prime number that's divisible by a whole number. So we know that prime numbers are divisible by only one in themselves, right? So basically they're not divisible by any other whole number. For example, 13 is prime since only 1 and 13 it's only divisible by 1 and 13, and every other whole number it can't be divisible by. But the thing is what are 1 and 13? Those are whole numbers, right? So what we see here is that the claim that a prime number is divisible by a whole number, that is true. In fact, every prime number is divisible by a whole number. So what Kieran was thinking is that when he said that primes aren't divisible by anything, he was thinking they aren't divisible by anything other than 1 and what the prime number is. So Josh is correct and Kieran is wrong in this case, just because he got the definition confused a little bit. All right, so that was a nice quick one. Let's go on to number 4. Is it possible for two different prime numbers to have a common factor besides one? Why or why not? So I have two different prime numbers, and we're talking about common factors. So just to recall what a common factor is, let's say I take the number 4 and the number 8, and we factorize them, so we know that 1 and 4 is a factor of 4, and so is 2. And we know 1 and 8 are factors of 8, and 2 and 4 are factors of 8. So their common factors would be 1, 2, and 4, right? Because those are factors that both these numbers have. So that's what it means to have a common factor. And this is saying, is it possible for two different prime numbers to have a common factor besides one? Why or why not? So just as an example, let's say I take two prime numbers. Let's go with 13 and 5. What are their factors? Well, their factors for 13 are 1 and 13, and the factors for 5 are 1 and 5. And again, you can check other factors to confirm that these are prime. But we see that, yeah, they're going to have a common factor of 1. And in this case, that's all that they have. So it would seem that this example might suggest that it might not be possible for two different prime numbers to have a common factor besides 1. But how can we know for sure using general reasoning and not relying on just a single example? Well, it might go as follows. Take two prime numbers, Mr. Prime and Mrs. Prime, and consider their factors. All right, so the factors of Mr. Prime are going to be 1 and then Mr. Prime himself. And then the factors of Mrs. Prime are going to be 1 and Mrs. Prime herself. So we know that they have 1 in common, but the fact that Mr. Prime and Mrs. Prime are different numbers means that those are not going to be equal to each other, right? So those are never going to be a commonality. And these are the only two factors of Mr. Prime and Mrs. Prime. And that's always going to be the case because they are prime numbers. Only 1 and itself are the factors of a prime number. So because of this, since these prime numbers are different than each other, the only possible factor that they can share is going to be 1. And the reason I did Mr. Prime and Mrs. Prime here is instead of just like saying two different numbers is because these are like stand-ins for numbers. They could be 13, 17, 19, right? So by doing this specifically for these kind of numbers that we don't actually know what they are, we're able to show that it's true for every single number. And this kind of thinking is something that's going to be very prevalent in algebra moving forward. I just haven't introduced the formalities of it yet. That's why I'm kind of like using things like Mr. Prime and Mrs. Prime, but we're going to be getting into the specifics where we can use what are called variables in order to model these problems a lot more nicely. But since this is a Fundamentals of Algebra series, I do want to start kind of pushing forward this type of thinking. All right, so I hope that made sense. And let's go on to the last question, number 5. Show that 3,692,103 is not prime. Okay, so we want to show that this is not prime. And the best way to do that is just to start by looking for factors other than 1 and itself. So is 2 going to go into this? Well, it can't because it's an odd number. Shucks. How about 3? Well, how do we check? We can add up its digits, right? So let's do that. 3 plus 6 plus 9 plus 2 plus 1 plus 0 plus 3. So 3 plus 6, that's 9. 9 plus 2, that's 11. 1 plus 0 plus 3, that is 4. So we have 9 plus 11, that is 20, plus 4 is 24. Is 24 a multiple of 3? Yeah, it is, right? 8 times 3 is 24. So since the sum of these digits is a multiple of 3, this number itself is divisible by 3. But that's a number other than 1 or itself it's divisible by, which means that this cannot be prime. All right, well, I hope you found that lesson useful, and I hope that you got a lot of good practice to really understand these concepts of primes and composite numbers. In the next video, we're going to be continuing this two-part series on the atoms of numbers by looking at something called the fundamental theorem of arithmetic, and it will really give us motivation as to why primes are the atoms of numbers, and it's going to show us how, given any whole number, we can build it using primes. All right, but I will see you then. Have a good one, stay groovy, and I'll catch you in the next video.